Okay, today we have Nicolas Heess. He's a research scientist at DeepMind, London. His research interests are artificial intelligence, machine learning, perception, motor control, and robotics. Prior to joining DeepMind, Nicolas was a postdoctoral researcher at Gatsby Unit, and he completed his PhD under supervision of Chris Williams at the University of Edinburgh. Nicolas, we are looking forward to your talk.
Okay, great. Yeah, thank you very much for inviting me. And I want to apologize in advance to sort of all the real roboticists here that I will have very few robots in my talk, unfortunately. It's mostly going to be a bit in simulation. It's going to be mostly in simulation, and if there's time at the end, we'll have perhaps some sort of results with actual robots at the very end. Okay, so basically, to set the scene and to show what motivates me and my work, I want to show a little video from the web, which shows an orangutan that in a zoo builds a hammock. So the animal first climbs up in the cage and ties sort of knots, ties a piece of cloth with a knot to the frame, and then it climbs into the hammock. And then in the second part of the video, it realizes that the hammock is actually too small. So it climbs back out, unties the knot, adjusts it, and eventually is happy. And sort of, I think the video really illustrates quite nicely what excites me, which is sort of, it's not just the agility and sort of the control over the body that the animal has, but also its abilities to sort of think about in the long term about its actions, to reason about what the consequences are, and of course to think about sort of its environment and to perceive it, etc. And basically recreating similar capabilities in artificial systems. That's sort of what I'm sort of interested in, and I'm working on this both in simulation, but also a little bit with actual robots. Maybe I'll just let this finish because it's too great. Okay, maybe I'll move on. So basically, what I've been working with in particular is RL in the last few years, although it's not really my background. My background is more probabilistic modeling. And it's a paradigm that has received a lot of attention in the last few years. In the essence, reinforcement learning, it's about learning by trial and error. It's something we do all the time. We try something, if it works, we do it again. And if it works, we do it again. And if not, we try something else. And the reinforcement learning paradigm formalizes this idea. We have an agent that acts in the environment with the purpose of achieving a goal. At every time step, the agent receives an observation, it takes an action, and receives a reward in response. And the agent's objective is codified by the reward, and the goal of the agent is to maximize the sum of future rewards. And basically, what's interesting about the paradigm are basically two things. The first one is that because learning operates by trial and error, it allows us to specify the goal of the learning rather than the solution. And RL can thus discover solutions that we couldn't come up with ourselves. Secondly, it can deal with long-term dependencies and delayed feedback. Rather than just looking at the immediate reward, the agent can learn to choose actions that lead to higher reward later. And this is obviously an important property for learning in the real world. We often need to do things that make us worse off or feel uncomfortable in the short term, but help us in the long term. Now, that's the theory, but in practice, there are actually a lot of difficulties. That starts with coming up with a good reward function that induces the behavior that is desired. Then we have the problem of credit assignment, exploration of local optima, algorithm stability. And if we think about learning in the real world, we have to worry about issues like data efficiency. We may not be able to observe the state, and we have to worry about the safety of our robots when they learn by trial and error. So what I want to do in this talk, I basically want to address different of these difficulties that I've outlined in the first on the previous slide. The first part of my talk will be mostly about how we can design reward and other incentives to discover complex behavior. And this talk will be mostly in simulation. And then in the second part of my talk, if time permits, I will talk a little bit about sort of data efficient algorithms for learning on robots in the real world. Okay, so, and please at any point in time, if you have questions, do interrupt. I'm very happy to take questions throughout the talk. So basically, the first part of my talk is really about a journey that started roughly 8 years ago when I started working on RL after my PhD. And this is sort of an example of some very simple results that I obtained then, from today's view, very simple, of an octopus arm reaching for a target. And basically, sort of this problem of motor control and learning motor control, if that's what you want to call this, sort of has stuck with me and fascinated me since then. And basically, out of this came a series of studies that have progressively worked up towards more complex behavior, sort of culminating in a coordinated humanoid soccer, which I'll try to work towards in my talk. It's something we just released a couple of days ago. So my talk is primarily going to be focused on these three studies, which are about building sort of complicated motor control and high-level task components in artificial simulated humanoids. Okay, so in 2017, we did a study that was pretty influential for me, which is sort of, I guess it's colloquially referred to as the Parkour study. And sort of the way this shaped my understanding of what RL can do for motor control is that it demonstrated that if you set up your environment right, if it has enough diversity and enough of a sort of curriculum property, then and even with a very simple reward function, RL can discover very complicated movement strategies. So we had tried before with different reward functions to induce jumping or nice running, and failed. And by just setting up the environment right, giving it enough of a curriculum, we were able to create basically complicated jumping, crouching, and other movement strategies for different types of creatures. You may have seen this before somewhere. So this is sort of transfer for a complicated humanoid to different terrains after training. The behavior is quite robust. Now, this was sort of exciting back then because we hadn't really gotten there before. The movements were considerably more complicated than anything we had produced beforehand, but they're also limited. So basically, the Parkour setup, it showed us that we can discover complex movements strategies if we can set up our environment appropriately, and sort of so that it induces diversity and helps with exploration. But sort of these tasks that we had there were still very short horizon. And for more complicated settings, setting up a curriculum like the one that we had in Parkour, where, for instance, you can simply make the gap a little bit wider, and then the agent would stumble more or less easily over this gap and learn to jump, was hard. So sort of the questions that sort of arose from this were, for instance, what would be a reward and curriculum for more complicated tasks, such as a manipulation task for a humanoid? How can we train agents to solve long horizon tasks that may require memory and perception? And how could we deal with multi-agent interactions and coordination? And this is sort of what I want to talk about in the next part of the talk. So basically what we set off to do was to create a learning framework that would allow us to not just firstly work with much more high dimensional humanoid characters, but also move beyond sort of simple movement tasks such as jumping, but towards tasks that would require memory and perception. So, and basically, what this made us think about is actually the different levels of structure that sort of we have in I guess embodied control. So if we think about like the suite of humanoid tasks here, sort of running around walls, jumping over gaps, foraging apples in a maze or carrying boxes around, we have structure at different levels of complexity, like just smoothness of the trajectories, cyclic locomotion patterns, but also goal-directed interactions with the environment. And basically, to solve complicated scenarios, what we need to be able to do is we need to be able both specify this behavioral structure using a reward or otherwise, or some other learning mechanism. And we need to be to be efficient. We want to be able to represent this movement structure, ideally in a reusable manner, for instance, in the form of skills. So the first step that we did was basically we set off to build a general purpose motor module that would support learning of high-level tasks that have a long horizon and that are less easily discovered than sort of the movements in parkour. And the main challenge there was to find a good trade-off between generality, something that wouldn't restrict movements too much, but also at the same time would rule out unnatural or undesirable behavior and would facilitate exploration appropriately. So the solution that we eventually converged on is what we call the neural probabilistic motor primitive. And basically what we did was we made use of sort of human prior knowledge in the form of human motion capture data. So we took data from the CMU database. We trained individual expert policies, to track these motion capture clips. And then to create a reusable motor module, we distilled all of those in a supervised learning step into a single sort of skill architecture. The skill architecture is effectively a latent variable. A latent variable model that you can think of as a conditional autoencoder. It models the action as a function of the current pose. And so the action is a function of the current pose. And to make this module controllable during training, we also condition on the future of the trajectory via an encoder. And this encoder basically maps the future trajectory onto the motor intention Z. And the action is thus a function of the pose, the motor intent, and this motor intention. And the motor intention can then be used later on as an action abstraction to control the behavior that this module produces. And this is sort of just written out what in math, basically the same what I've just said. So once trained, this motor module can be used as part of a policy to solve a high-level task. So this is this motor module here, and that it can be composed with a high-level policy that takes in vision information and may have memory or anything else that is task relevant. And this motor module takes in proprioceptive information. We tested this on a number of sort of visual motor reasoning tasks, if you like. So in this task here, the humanoid needs to identify in every episode which color apple is edible. In this case, it were the red apples, and then it needs to remember and find all the other ones and then avoid the ones that are not edible. So basically, in this task, a sparse reward plus a motor module leads to effective exploration. It constrains the final behavior to be human-like, and it allows us to solve long horizon tasks from sparse reward that would otherwise be difficult to solve. And here's just another example of the same approach and action in sort of a maze navigation task also from egocentric vision. So it's the agent view here, and it needs to collect all the apples in the maze. Okay, so this motor module and random exploration and skill space plus a sparse reward led to rather naturalistic behavior and task success on these sort of long horizon visual motor reasoning tasks. So with sort of having that figured out, basically we then wanted to move on to more challenging goal-directed movements. And one movement that's significantly harder than basically these exclusively body and locomotion movement is object interaction and manipulation. They're harder because they're intimately coupled with the environment, and they require perception and or tight perception action coupling. And from a learning perspective, they also constitute a much harder exploration problem, since random movements, even if they are sort of smooth and reasonable, will not sort of by chance lead you to pick up a box, for instance. So the way we tackled this was, so what we wanted to, our sort of our benchmark was to solve two tasks like this, like a warehouse task where the humanoid needs to pick up a box and move it to a different pedestal as instructed, or a catching and tossing task where it needs to catch balls and then drop them into a box. The way we tackled this was that we sort of collected a set of dedicated mockup data of manipulation and ball catching and throwing tasks. So the figure that you don't see here is actually a colleague of mine who catches the ball and throws them back. And we collected sort of 90 minutes of diverse data where the boxes were positioned at different heights. The boxes had different sizes, and where we had sort of whether the actor had to interact both with balls and with boxes. We then took effectively the same approach as we did in the previous study. So we took the motion capture, we trained expert policies to sort of execute these these carrying and catching movements. Those policies were conditioned on the box and the ball position. And then we distilled them into a motor module. The important choice that we made here, and this is something we hadn't really thought about before, but then became apparent as a potential problem, was that the motor module, we chose it to make, we had to choose whether or not to make it object aware. We chose it to make it not object aware. The motivation for this being that this would give us an advantage in terms of generalization. We wanted the module to be operational in any scene with an arbitrary number of objects. So we had to sort of make that choice. We chose to make it not object conditional, which had the disadvantage that this module would then not lead to spontaneously interesting goal-directed exploration. So to be able to solve tasks like picking up boxes and carrying them around, we used two additional ingredients. And in particular, we used our demonstration data again effectively as a form of high-level demonstration by initializing the humanoid at the character at the beginning of an episode in suitable poses derived from the motion capture data. So in some episodes, we would initialize it close to the pedestal or with the box already in the hand, like in these two figures, or in other poses. And we also used the curriculum of different box sizes, weights, and pedestal heights. And this combination, together with the motor module and sort of a slide shaping reward, then allowed us to train characters to solve this warehouse task, but also the catching and throwing task. So here's a video of the final result. The left-hand side is again the agent view, so from the egocentric vision. The right-hand side is a third-person view. And the same module was usable for both. After training was usable for both sort of the box carrying tasks and the catching and throwing task. And basically, we were able to extrapolate the movement skills beyond what was originally in the motion capture data by expanding, by sort of gradually adjusting pedestal heights and sizes. And once trained, because the agent had egocentric vision, it would also naturally generalize to other scenes. And sort of, for instance, with more boxes, or it would be able to catch boxes instead of balls. So I think this is also an interesting insight that basically these physically embodied characters with appropriate perceptual space can generalize to novel scenes quite naturally, which is something one might not easily expect. Okay, so the insight from the study here was that a motor module can constrain the movement space, but for more complicated tasks, such as manipulation, just having a random exploration in this motor module, sort of in this movement space, is often not enough, and we needed additional strategies like the episode initialization, or a form of high-level demonstrations, if you like, to make learning succeed. So, and this then, so this was great from our perspective. The movements were perhaps not as smooth as we would like them, but still, having figured that out a few years ago, this seemed quite out of reach. We then wanted to move on. We had achieved sort of controlling the humanoid characters on long horizon tasks. They were able to execute goal-directed movements and perform interaction sort of in a where the agent needs to respond differently in situation and possibly others. As a benchmark, we chose soccer, and the idea is interesting. It's not the first.
Nicolas?
Thinking for a long time. For us, it was interesting. Yeah.
I think there is a problem with your connection. We can hardly hear you now.
So basically, what the previous results had shown us were how we can solve long horizon and goal-directed movements, including ones that involve environment interaction, perception, and memory. But what we hadn't shown yet was, or what we hadn't achieved yet, that we hadn't our characters yet embedded into diverse tasks where the agents that really have sort of structured multiple different sort of temporal and spatial scales, and where the agent needs to respond differently in different situations, and possibly even interact with other agents. And sort of to go one step further, we chose soccer as a benchmark. And we are not the first ones to sort of recognize that soccer is interesting in this regard as a closed world with a lot of richness. So the RoboCup community has obviously known this for a long time. And just to make this a bit more clear, what makes soccer interesting is that if you think about it, you really have structured at least sort of three different levels of abstraction. So you have just basically controlling your body, like getting up and running. You have the problem of like sort of goal-directed interactions with the environment, ball control, dribbling, shooting, and then you have sort of the high-level structure of sort of winning the game while interacting with your teammates and opponents, achieving coordination, passing, blocking, and things like this. Right. And it's also interesting to think about this, that even though these different levels of abstraction, they may seem quite natural to us, they're actually not well defined at all. So this is unlike, for instance, playing chess with a robot arm, where you have two very well defined sort of and well separable levels of abstraction. Soccer has very different properties. And I think this makes it an interesting test case for studying sort of multi-scale control. Which is what we were interested in. So basically, this is some result that we released just a couple of days ago. We have trained humanoids to play soccer, and this is just a little teaser, and then I will explain sort of how we did this. Okay, cool. So right, so we created a game that was a very simplified version of soccer, both to keep it computationally more tractable on the simulation side, but also to make the learning a bit easier. So the game consists of 4 players, 2 teams of 2. The characters are the same that I've used in the previous examples. They're 56 degrees of freedom. And basically, the players can leave the pitch, but the ball bounces back. And the goal of the match is to score as many goals as possible. And the approach for solving this task consisted basically of three ingredients. The first one is a gradual skill acquisition. So we first learned low-level movement skills. We then trained based on those mid-level soccer skills like running, turning, dribbling, and kicking. And finally, trained the agents to sort of achieve goal-directed and coordinated soccer gameplay. To do that, we use different types of learning signals for different parts of the learning process. We used imitation learning, or learning signals, or sort of reward specifications, if you like. We used imitation learning for the low-level movement skills. We used reinforcement learning with well-defined reward functions for the mid-level skills like dribbling and shooting, for instance. And then we used multi-agent RL and self-play to discover sort of interaction strategies and more complicated sort of context-dependent movement strategies at the high level. And finally, we used two types of skill representations during the learning. First, we used our motor module again to restrict sort of the movement skills of our agents. And then we used behavior priors for mid-level, to represent the mid-level skills. And sort of one particular thing we were sort of quite wary of was to sort of use skill representations that would basically allow for efficient learning, but at the same time would not overly restrict the flexibility of the final behavior, which is often a problem when sort of with sort of hierarchical representations. So the pipeline at a high level sort of looks like this, and it's a bit daunting. I will walk through this step by step. So we first have a phase of learning the low-level movement skills, which involves motion capture data. We then train mid-level skills using a set of training drills and distill them into behavior priors. And then we learn the full gameplay with multi-agent reinforcement learning, regularizing the behavior with the low-level movement skills and these mid-level drill priors in the third stage. So the first stage basically corresponds to what I've shown before. We got some dedicated soccer motion capture data from free soccer play and sort of trained agents to track these clips. We didn't track the ball in this case, so it was literally just the movements. And then we distilled them again into a sort of low-level motor module, just in the way that it described before. So we have an encoder of the future trajectory and the proprioception that goes into this low-level controller, into the NPMP. And then in the second phase, we chose a set of training drills following a target, dribbling, kicking, and shooting. And we trained individual players to succeed at these drills. So this is for instance the outcome of a kick to target drill. So it's like soccer golf, if you like. And here is the agent trained to dribble a ball, basically. And the whole point of creating these mid-level skills was to facilitate exploration in the full game, because our movement model, so the NPMP, is very general and doesn't restrict the movements sufficiently. Okay, so we trained our expert policies on those tasks using the low-level motor module that we had produced before. They received proprioception, the information about the drill and context, like the ball. And then one problem that sort of arose from this is that these expert policy would depend, for instance, on the target specification, but that is not available during the soccer play. So to make those experts reusable in the full game, we distilled them into what we call drill priors, basically by learning to imitate the behavior of these experts when they're following a target, for instance, but not giving those drill priors exactly that information. So this can be done basically by through a form of behavior cloning or distillation. And the outcome is basically a policy that, for instance, dribbles, but sort of spontaneously changes direction without following a particular target. So that you can think of this as an abstract, as a very concrete representation of a dribble skill. Okay. And then finally, in the third stage, we used multi-agent RL to learn the full gameplay. Now, high-level strategies in this game are quite hard to handcraft or to specify via a reward. And what we therefore did was basically we sort of exploited the power of multi-agent self-play, where sort of complex solutions emerge through a form of arms race between learning agents. We had a population of agents, and we sort of repeatedly create matches, pitching those different agents against each other. This was also combined with an evolutionary strategy to improve the overall skill level in the population. The population self-play itself was not sufficient to lead to good learning performance, but we also needed to shape the behavior of the agent using different tools. So the raw task is very sparse reward, very high variance, scoring a goal. So we used 3 shaping mechanisms. Firstly, we used the low-level skill module that we had produced in the first phase. And our soccer players sort of were trained to produce actions through choosing motor intentions for this low-level motor skill module. We then used a set of, and that basically constrained the behavior that the agents could learn. We then used shaping rewards to sort of shorten or to simplify the credit assignment and shorten the learning horizon. So for instance, like a reward for making the player go to the ball, or a reward for having the ball a high velocity, for the ball to have a high velocity towards the goal. And finally, we used our mid-level skills to shape the behavior of the soccer players. And we did this by introducing basically a regularization where we kept the agent's behavior close in terms of KL to the behavior specified by a mixture of these priors. And that again served to facilitate exploration and as a sort of more proximal learning signal. And one way to think about what we did there was basically that we augmented the reward with a KL regularization or shaping term. And the effect of this is basically that if you imagine this to be sort of the behavior space or the trajectory space, and this is the region that's that is favored by the reward, then basically the prior favors this region, then a good solution lies in the intersection. So you can think of the prior basically as restricting the search space for good trajectories, or pulling the agent towards meaningful parts of the trajectory space. In our case, since we had multiple priors, actually, so from dribbling, following, and kicking, and so on, we chose to construct a mixture of those. And the effect of this was that you can think of this in terms of probabilistic models, that basically the agent got to adaptively switch between different priors depending on which prior was in the current situation the most appropriate one. So rather than constraining our agents to follow an average behavior of all priors simultaneously, which clearly doesn't make sense, sort of this formulation allowed them to switch between dribbling and kicking and following, or just running and turning, depending on the situation. Okay, so this was the pipeline, and overall, I just show some highlights here. So this visualization shows basically which agent has or which team has control of which part of the pitch at any point in time. But overall, the training pipeline that we set up led to the discovery of not just robust and fairly sophisticated movement skills, but also sort of coordination and a form of turn taking and adaptive roles, where, for instance, agents discover that if the teammate is already on the ball, they shouldn't go there, but they should sort of run into this space. And I mean, these behaviors are clearly still sort of Mujoko-like, but they are overall, I think, surprisingly naturalistic. I'll just let this play for a few seconds. So one thing we didn't observe, unfortunately, was sort of really very deliberate passing, where one player would to the other player and that other player sort of more carefully. But it's also not entirely clear whether the sort of the setup that we have here really encourages this. Can you still hear me?
Yeah, I think, again, we have a bit of problem, but I think it's fine.
Okay, let's carry on.
Yeah.
So I'll stop the video here. It's on YouTube. We did a sort of fairly thorough analysis of the behavior that the players learned. So one interesting thing that we found was, for instance, that the players first learned to move and interact with the ball, and then later on they learned to pay attention to other players and learn to coordinate. There was sort of a clear sort of timeline in how they discovered different types of behaviors. We have found that the player's internal representation clusters observations according to the high-level properties of the game, much more so than this is true for the raw observation. So they form a relevant sort of representation of the game. The player's performance also correlated with whether they were able to predict the future of the game. And this is sort of something that people have found in studies of human soccer players, for instance, as well. So that this type of prediction is important. And we did find that players indeed adaptively made use of the different types of mid-level skills that we had represented via the behavior priors. Yeah, and that's basically the conclusion of the first part of my talk. So I've presented a series of studies where how we went from sort of basic movement skills to sort of longer horizon visual motor reasoning tasks, sort of goal-directed, complicated interactions with the environment, and finally sort of soccer as a benchmark or representation, or sort of a case study of multi-scale control and also multi-agent interaction. And the challenges that we sort of tackled as part of this series of studies are those of behavior specification, exploration, credit assignment, and diversity, and the solution elements that we used in different ways in different parts of in different studies, sort of learning from imitation data or handcrafted rewards, self-play and population-based training for discovery of complicated strategies and sort of achieving sort of robust and diverse strategies, multitask or stage training, and also different types of skill representations like a hierarchical one, the motor module, or the behavior prior. And I don't know where are we now in time. I guess there are 10 minutes left. So I have a second part, but maybe we should stop here. It's sort of, what do you think makes most sense?
Yeah, I think it makes sense to see if there are some questions.
Yeah, I think so.
Okay, so can I start, Arbut?
Please.
Yeah.
So I have a question about going from mocap to motor control.
Mm-hmm.
So do you do here, and so you said that you don't have any kind of reinforcement learning here, and you do only imitation learning. So how do you make sure that these motions are physically possible actually when you do imitation learning?
Sorry, this was, maybe I should have worded this more carefully. So this is sort of the imitation is a form of a reinforcement learning. but it's reinforcement learning with a very tightly constrained reward that sort of forces the agent to track the reference trajectory very closely. So in that sense, it is still RL, and we have to experiment with different versions of this. But it's RL to do imitation with a very tight sort of error on sort of joint positions, for instance.
Mm-hmm. And how tight how diverse the set of motions from the mocap should be?
Well, the more the better in general. Although
but here, what did you use?
So for the manipulation task, we had like 20 minutes, I think, of data, if I remember this correctly. I don't know exactly how much we had for the first and the last studies that I showed. I can find this up, but find this out. So something I think between probably, I think for the manipulation task, because we specifically collected that data, it was probably the smallest amount of data. And I think in all cases, it was probably less than 2 hours. But yeah, more data is generally better, although at least in our hands, and I think probably different people will get different results, you have to be careful about balancing the data. So because of the way we train this motor module, it's sort of distilled to produce any of the behaviors in the training data. If you over-represent one type of movement, it will have a harder time, or an agent later on will have a harder time of discovering other types of movements that are because they'd be underrepresented and therefore perhaps less emphasized in the motor module. Does that make sense?
Yeah, thanks.
Sorry.
Hi, yeah, thanks a lot. I really enjoyed. I'm very impressed by the coordination you managed to get. I have two questions. So one is more maybe about because I'm very much interested in robotics. When I see the football player, it looks to me that there's a lot of motions that that it seems would be very hard to put on a robot. And I was wondering what kind of physical simulation you use, and how do you look into constraining the amount of torques that you can apply and contact forces that you can have on the ground. So that's the first part. And the second part, I was wondering, how do you define the model primitives that you decide? So you say the middle level is going to have dribbling and a certain number of things. In the low level, you have more basic primitives. I was wondering if there was a methodology to decide what are these primitives, because that would be very nice to be able to scale that to robots.
Yes. So for the first question, we have, to be honest, I've forgotten some of the details, but we have not made an effort of making. So I think the way the humanoid is designed is such that the torques are roughly reasonable and the friction is roughly reasonable, but we do not penalize contact forces or anything like this. So it's not designed to be a physically like realistic simulation that would be representative of sort of a real robot scenario in this case. But I do think we have made some effort of making the character not like crazy strong, for instance, and that actually makes the learning problem then quite a bit harder, unsurprisingly, right? Because it has to actually have more foresight in the way it moves. So with regards to your second question, I think it's a very interesting one, and basically so far it's something we're still sort of actively looking into. I don't have a very good answer. I mean, so far we've basically worked with 2 levels of abstraction, or 2 levels of behavior specification only. So there's the basic movement, and the basic movement only depends on the body for now. And then for soccer, and sort of this is sort of what I was trying to say when I was talking about the manipulation task in particular, that motor module is very generically usable, right? But it doesn't actually know by itself how to interact with objects because it can't see them. So this is then information that you need to externally provide to use that to solve a task. And for soccer, we basically handcrafted, or we chose, for instance, that the dribble prior that this would know about the ball, but not about other elements of the scene. And as an example, for instance, and similarly, you could imagine a passing prior, like as at the next level, that knows about the ball and perhaps a particular teammate, right? But then you already run into problems because sort of how do you, like, if you have multiple teammates, which teammate is it then? So you need to think about the nature of the representation of your environment in this setting. So I don't think I've got a good answer, but I think it's indeed a very interesting question of how you should structure this. And I think there are two things you need to think about. The first one is what kind of representation is what kind of observation representation is even transferable across different settings. So vision is great because it's generic, right? It can apply to any scene, but then you have to watch out for, I don't know, changes in color and lighting, etc. Right? And it's also much harder to make a movement independent of other elements in the scene. If you work with features, you have sort of more specific worries. So it's the observation representation that you need to think about, and then obviously what kind of behavior abstraction makes sense for the specific scenario that you're in, just from a functional perspective. And we don't have really we don't have a very good paradigm here. I guess what we were trying to do with the different mid-level skill priors for soccer was to just provide a menu of different choices from which the agent could then choose adaptively during learning. So is this at least a partial answer to your question, even though maybe not super satisfying?
No, this is great. I was, because in robotics, it's been maybe 30 years that people have been talking about like the notion of motor primitives and really trying to break down, movement into like, pieces of primitives you can use. And it seems that it's very related to what you're doing, except that you took it to another level because you can really compose them. So I was just curious to know how you thought about it. But I think this is great. Thank you.
Let me actually add one thing that now that I'm thinking about it. So maybe the paradigm was in some ways that the low-level movement module is as general as possible. It's a hard constraint on what the agent can produce, right? Because the actions are actually produced by that module. So what's not in the module cannot come out. So that's a hard constraint. So we keep it very general. And then at the next level up, we have these priors, which are sort of more a form of soft regularization with a cost term. And because then there's no hard constraint that you impose on the behavior of the agent. Those can be a bit more specific because the agent, if they are not suitable, it can still deviate from those, right? So we have this very generic, general purpose module that is a hard constraint, and then more specific ones that can provide guidance, but those are sort of soft constraints. So this isn't a specific way how to choose anything, but it, I guess, is an architecture that overall has a fairly good flexibility, or has the chances of having a good flexibility.
Thank you.
Okay, thanks a lot, Nicolas. Unfortunately, we should stop the conversation here because we need to start the next talk. Thanks again. We really appreciate the talk, and hope to see you during our panel session.
Yes.
Thanks a lot.
Thanks.
Nicolas.
Sorry about the problems with my internet.
No problem.
I don't know what is.